Hello, everyone. Welcome back to Codex. Today, we're happy to feature a talk from Jose Israel Rodriguez from the University of Wisconsin. Professor Rodriguez is an expert in applied algebra and applied algebraic geometry. Today, he'll be speaking about activation, degree threshold, and expressiveness on the polynomial neural networks. Before we get started, a couple of quick announcements. This talk is being recorded. So if you would like to ask a question during the talk, just go out. You are welcome to go ahead and unmute yourself. But if you don't want your voice recorded and on the internet, you can type your question in the chat and one of the organizers will ask the question for you. Alternatively, there will be an unrecorded question and answer period that is after the talk. If you're not asking a question, we do, however, ask that you keep yourself muted in order to ensure the audio quality for everybody. That's it for announcements. So take it away, Jose.
All right, so thank you all very much for taking the time to attend this talk or to watch this talk if you're from the future. I'm very excited to share a project with you that I like more and more. And my goal is to present some work on the expressive power of PNNs, as was mentioned, and these are known as polynomial neural networks. So I'll mention from the start that this is joint work with my wonderful collaborators. So Bella Finkel is a graduate student at UW-Madison. She has a background in physics and currently working on optimizing cool functions on cool varieties. Thomas Yale is a postdoc at UW-Madison. I've known him for a long time. He's a toric geometer, and we did some polynomial system solving work in the day, or a while back. And Chen-Si Wu is faculty at UW-Madison. His office is right down the hall from mine when I'm on campus. Today I'm not. We're doing Zoom. And he has previous work on Rayleigh functions. But today's talk is about polynomial neural networks. So let's say a little bit about that. So I'll kick things off by putting this into a broader context of neuroalgebraic geometry. So the theme is polynomials appear across machine learning. And so because they appear across machine learning, you get a nice dictionary between machine learning topics and algebraic geometry concepts. So the ones I'll focus on today are underlined. So expressivity in machine learning is related to dimension in algebraic geometry. And our main tool for making this, for using this connection is identifiability and invariance being connected to the fibers of a parameterization. So that's an algebraic geometry concept, and we'll see more about this later. So if you like some of the things that I've said already, you'll definitely like this invitation to neuroalgebraic geometry, this 5-author paper that goes into detail for a lot of these concepts. In terms of applications, polynomials appear in machine learning, all kinds of applications. One I'll highlight is facial recognition that was work done by Gugorois, who's faculty at UW-Madison. But the theme is that polynomials can be used to model higher order interactions between inputs. So I won't speak to the applications today. Today, I'm really focused on the expressivity question. What types of functions can these polynomial neural networks that I'm describing in a moment can describe? So let's get into that. So what do I mean by a polynomial neural network? Well, one of the tools that we'll use to study these are architecture and activation degrees. So I'll say what these concepts are as well. So Zoom had a lot of pop-ups. Okay, I had to clear that. Here we go. So invariance and expressiveness questions. So with math, I like to be motivated by questions. So let's start off with 2 questions. So the invariance question is which weight matrices map to the same polynomial. So where did this polynomial come from? Well, here we see a neural network. It has 3 inputs, a hidden layer with 5, and 1 output. So if we take some weight matrices, we want to map them to some function. According to this architecture, these weight matrices are 3 by 5 and 5 by 1. 5 by 3 and 1 by 5. Sorry about that. Forgot the transpose. So, okay, so these weight matrices map us to a polynomial function. There we go. And so how does this work? Well, we have our 3 inputs, this vector here, and we hit it with our weight matrix to get 5 linear functions. Now, my activation function now takes each linear function and applies a nonlinear function to it. And the nonlinear function I'm interested in is the squaring map. So I take my linear function, I square it, I have something nonlinear now. Well, I don't have to just consider the squaring map. I could put any exponent here. So if I choose exponent r, I would then get a polynomial of degree r. And this is related to this exponent here. So my parameter map takes weight matrices, and depending on how I choose my activation function, I get some polynomials of degree r here. If I continue on to this last part of the neural network, I get a linear combination of these 5 quadratic functions to get a single quadratic function at the end of the day. So what happened? We took weight matrices, mapped them to a quadratic function. And the invariance question says, can you find other w hats that map to the same polynomial function? All right, so that's invariance. Can you find other weight matrices that map to the same function? That's invariant. Expressiveness is different. It says what kind of functions can be described by different choice of weight matrices. So if I consider all possible weight matrices, I'll get a family of functions in the output, and this family of functions is known as the neuromanifold. So the neuromanifold is the image of this parameter map. The neurovariety is the Zariski closure of this parameter map. So it's the smallest algebraic set containing the image. So our problem is to understand the dimension of this image, because this gives us a handle on how expressive our neural network is. In particular, if we make different choices of R, does it happen that we get different dimensions? And the answer is yes. Depending on your choice of R, you get a different dimension of different dimensions of neurovarieties. And so we want to understand how this, what dimensions appear. Okay, so at the end of the day, the goal of this talk, or not the end of the day, in like 40 minutes, the goal is to leverage algebraic geometry. We want to describe fibers of this parameter map. We want to answer the invariance question, and we want to describe the image of the parameter map. We want to describe the expressiveness by knowing its dimension. So let's keep going. So activation degree thresholds. So is the dimension expected eventually if we take R to be sufficiently large? So here's the first illustration of what I'm talking about. So in this slide, we are fixing the architecture to be 3, 2, 1. So we have our input layer of width 3, our hidden layer of width 2, and a single output. So if we plug in our weight matrices, we get a function in 3 variables, and it's just a single function because we have one output here. If we choose our positive integer, r, then our weight matrices are going to a polynomial of degree r. So we have 8 parameters, because here we have a 3 by 2 matrix, here we have a 2 by 3 matrix, here we have a 1 by 2 matrix, so we have 8 parameters total. So these 8 entries of the weight matrices give us a polynomial of degree 2. So this polynomial degree 2 sits inside of a finite dimensional vector space, which sits inside an infinite dimensional vector space of all possible functions from R3 to R. So if we don't want to consider just positive integers, if we want to get away from polynomials, say we want to take R to be a half or a third, if we're doing square roots or cube roots or any positive real number, then let's restrict our choices of weights to be positive. That way we don't run into issues of taking square roots of negative numbers. And we get functions that map the positive orthant or non-negative orthant to the non-negative orthant. Okay, so I've changed my parameter map a little bit. Instead of just restricting myself to positive real numbers, or sorry, to just integers, we have now positive real numbers. Okay, well, this function space is a mess, and so way too complicated. So let's try to bring it back to a finite dimensional vector space. And how we can do this is by choosing 6 random points in R3. And I'm going to have the evaluation map that takes a function in our function space of mapping R3 to R. So if we take a function in here, we go into R6 by just evaluating our function at these 6 points. So that's the evaluation map. And now you might guess, well, let's compose these. So if we first do our parameter map that takes our R8, so this complicated space, then we do the evaluation map to take the complicated space to R6. Now we have a map from the R8 to R6. So this leads us to this nice 6x8 Jacobian matrix. So here I chose the Z1, Z2 to Z6 points really nicely so that the Jacobian matrix is easily described on a slide. And what we should focus on is the left block. So this left block here is JR, and it's a 6x6 matrix. And so this Jacobian matrix, the 6x8 Jacobian matrix, will drop rank, turns out, when this 6x6 matrix drops rank. So we can plot this. So if we plot the log of the absolute value of the determinant of this 6x6 block, we get this red curve here. It's a red curve on my screen. I think it's red on everyone's screen. So at this red curve is the value of the log determinant of the Jacobian. And so what's happening is that these orange dashed lines, when r is equal to 1, we see it's the Jacobian is dropping rank. When r is equal to 2, the Jacobian is also dropping. And then if we extrapolate from here, maybe never again will the Jacobian drop rank. And so this is what we're aiming to describe. We want to know for which choices of r's will the Jacobian drop rank in this example. Why do we care about this? Because this allows us to determine the dimension of the neural manifold. Okay, I'll pause here in case people want to shout out questions. Otherwise, I'll keep on going. All right, so we go onwards. So one question that we could ask is, well, here the Jacobian dropped rank. Is this expected, or is this what we would expect to happen, or is something special happen? And that's what I want to describe next. How to characterize, how to show you why when r is equal to 1, we expect the Jacobian to drop rank, versus when r is equal to 2, we don't expect the Jacobian to drop rank, and this is a defective situation.
Excuse me, Jose.
Yes, go ahead.
Is the rank always an integer here?
No. Oh, sorry. The rank is always an integer. Here, I am plotting the value of the determinant. So if the value is non-zero, then if the value of the determinant of the Jacobian is non-zero, then it's full rank, rank 6. Here, I'm plotting the log. So long as I'm not going off to negative infinity, then the rank is going to be 6. Does that answer your question? Or you can ask me again.
Yeah, no, that 100% clears up my confusion because it looked like you had a continuously valued rank and now you, okay, yeah.
Yes. I do not have a continuously valued rank. That would be problematic. I have a continuously valued log determinant, which when it's non-zero gives an either rank or full rank. Awesome. Other questions? All right, so the next thing is invariance being connected to the expected dimension and defects. So in the polynomial neural network literature, there's this multi-homogeneity lemma. So for all invertible diagonal matrices and permutation matrices, I can give you some invariance. So here I pick W1 and W2, I plug them into my shallow neural network, and I get a function. Well, what are the choices of W1 and W2 hats? Do I get the same function? Well, I don't know all of them, but I can tell you some of them. And one possible choice you can make is you pick D to be invertible diagonal here, you pick P to be some permutation matrix, and when you apply your neural network, when you do this multiplication and you place that as your first weight matrix, you want to undo what you just added in or multiplied through, and that's undone by here. You take the invertible matrix to the minus rth power and multiply by this transpose of the permutation, its inverse. Now, why do I mention this? I'll tell you why in a second, but the important definition is expected dimension. So for the neurovariety, VDR, it has an expected dimension. And you would guess the expected dimension is the number of parameters. So D0 times D1, the number of entries of this matrix, plus D1 times D2, the number of entries in this matrix, But because of this invariance, we have D1 entries that are along the diagonal of this big D matrix. We need to subtract off that many degrees of freedom. So the expected dimension would be this number. And then what is this thing? This is the size of the ambient space, the dimension of the polynomials of degree R in D0 unknowns. So the expected dimension is the minimum of these two quantities. And you're defective when this difference, expected dimension and actual dimension, is positive. Okay. So if you fix an architecture, if there exists some capital T where the defect is 0 for all r's larger than t, then this is some threshold where the neurovariety has the expected dimension. So it was conjectured by Khalil, Traeger, and Bruna in their NeurIPS paper that the activation degree threshold exists for any architecture, or what they described it as. Really, how they described it is that the neurovarieties are non-defective for large enough R. So let's see an example to carry this through. And this example, even though it's a shallow neural network, these ideas also work for deep networks, which I'll just state at the end, but we'll get into details about. So in case the first picture was too small, here's the big picture with our input layer, 3 nodes here, our hidden layer, and our output. So we have one polynomial and 3 unknowns. So if R is equal to 1, we can remember our parameter map. So we take our weight matrices. These get mapped to this polynomial function here. If R is 1, this is a linear function. And so we get a linear function. No matter if we went through all possible choice of weight matrices, we could express any linear function. And so the space of functions is 3-dimensional. So our neuromanifold for the 3-2-1 architecture, when R is 1, is 3-dimensional. You can, if you wanted to brute force this, you could set this up using your favorite computational algebra solver. And at the end of the day, you would see that there are no algebraic relations, that these coefficients need to be satisfied. And so it's full dimensional. Okay, so that's for linear functions. Let's keep on going and now see the quadratic case. So in our running example, R is equal to 2, this turns out to be a defective situation. So here again, we have our parameter map that takes weight matrices and maps them now to quadratic polynomials. So when R is equal to 2, we pick our weights, and they are some homogeneous quadratic polynomial here. We could run our favorite computational algebra software, and you could find out that these coefficients will always satisfy this polynomial relation. So how did this coefficient come from? Well, if you chased it through, you would see W200 times W11 squared is equal to C200. Oh, sorry, we need to add to it W201 times W11 squared. That would give you the coefficient of X1 squared. All right, in either case, so we have 6 coefficients. So our ambient space of quadratic polynomials and 3 unknowns is 6-dimensional. We have 1 algebraic relation, so our neurovariety is 5-dimensional. So it's 1 less than expected because the expected dimension is 6. So that what happened here is there are extra invariants than just the multi-homogeneities that were predicted or that were described earlier. Okay, so let's maybe try to give a visualization of what's going on here. So the neurovariety that we just found out is 5-dimensional. So here it's an algebraic equation that cuts out the neural manifold. So this 5-dimensional space is inside of the space of quadratic forms and 3 unknowns. Quadratic forms and 3 unknowns, you can think of these as 3x3 symmetric matrices. If we look at the determinant of this 3x3 matrix here, and these are the coefficients of our quadratic form. This gives you this algebraic expression here. So this is a global description of the neural manifold. It's 5-dimensional, so it's hard to visualize. Here, I picked out some slices for you. Maybe I can try to see, yes. So in this 5-dimensional world, I can vary some parameters, and I can sweep out some 2-dimensional surfaces in this 5-dimensional world. And we see that this is, I don't know, pretty curvy and not so, yeah, it's complicated. But with the global description, we see it's cut out just by this quadratic. And what's also cool, what is also cool, here we go, intersecting this figure. So we have these slices of the neural manifold. What this global description tells you is that if you were to intersect a line with this figure here, you're going to have exactly 3 points of intersection. This is related to the degree of the neural manifold, and I won't speak about this at all. I'll just mention in passing that this is, in some sense, why do I say it's a global description? Because no matter how you choose this line, when you stab the neural manifold with it, you can only get at most 3 points of intersection. And I double checked this because to me, when I first looking at this, it's like, oh, maybe I can get like 4 or 5 points, but no, you can only get 3 points of intersection. So there are no typos in my code. Okay, if people have questions, now's a good time. Otherwise, I'll take a sip of water and keep on going. All right, so we focused on 2 neural manifolds. One was easy space, just linear functions. Another was a subset of quadratic functions. I want to now describe the dimension of any neural manifold of architecture 321 and activation degree being some positive integer. And so if my integer is large enough, so if I take a high enough degree, then I can give you a precise description of the dimension of the neural manifold. So how does this work is that we prove this lemma. So this lemma says that if you let P1, P2 to Pk be any multivariate polynomials that are pairwise non-proportional, okay, so not any, but any that are pairwise non-proportional, meaning you can't find some non-zero or some alpha and c, a real number if you prefer, such that one polynomial is a scalar multiple of another. So these can be linearly dependent. So if you had many polynomials, you'd expect them to be linearly dependent here if they were all linear functions, let's say. But no matter how many of these you choose, if you take R large enough, then they're going to be linearly dependent. Oh, sorry, linearly independent. Or in other words, if you had this relation here amongst the powers of the polynomials, so now they're linearly dependent, then R can't be too large. All right, so this is the lemma that we use to prove a result. So how do we apply this? Okay, now it should be a proposition. So how do we apply this lemma / proposition? Well, we use 4 polynomials. So here, our parameter map gave us a single polynomial output. How do we get 4 polynomials from it? Well, we look at what's inside the parentheses. This is our linear function. This will be P1. This is a linear function. Take it to be P2. All right, so we're halfway there. So what we're interested in is describing understanding the invariance question. So we want to know if I pick some random choice of weight matrices, I get this function here. What other choice of weights allow me to describe this, or get me the same function exactly? All right, so what we see here is a relation amongst powers of polynomials. So our P3 and our P4 are going to be here and here. So P3 is this linear function, P4 is this linear function. So because these are randomly chosen coefficients, P3 and P4 are not going to be proportional. With a little bit of work, you can prove that P1 and P2 can't be proportional. And at the end of the day, by this proposition, it turns out that you must have this proportionality between these polynomials here. So the invariance is completely described by multi-homogeneity. That's the point I'm trying to make here. So we've described the fiber of our parameter map completely. And because we've described the fiber completely, this allows us to use algebraic geometry to give us the dimension. I'll say this theorem in string of ideas. No. Before I say the proof ideas in general, I'll highlight our main results. You can ignore the theorem and just focus on how to interpret it as a result. If your activation degree is sufficiently large, then the dimension of the neuromanifold is expected. In particular, it is this quantity here. All right, so earlier we had this minimum of 2 numbers when we were looking at expected dimension, and here I've narrowed it down to 1. And the reason why I'm able to narrow it down to 1 is because as your activation degree gets larger and larger, your ambient space gets huge. It's the space of polynomials of degree large R and D0 unknowns. And so this space of polynomials gets gigantic, but these weight matrices, they all stay the same size. And so you're just going to have this number of parameters of the number of the entries in the weight matrices modulo this invariance that we saw, or multi-homogeneity invariance, to get you the expected dimension. So the point is that you have a small dimensional neuromanifold in a huge ambient space, and we give you the dimension of that. So how does the proof work? And so the proof relies on the previously mentioned lemma/proposition, as well as this theorem, which involved the use of Wronskians. And so what this theorem is, it's a theorem involving rational functions and just one variable. So if you're looking at n, your n is now the power, and you have R1, R2 to Rk being rational functions that are non-constant. It's important. So if you take these rational functions and raise them each to the nth power, and if they add up to 1, so you add them up to get the constant function 1, then if this happened, n can't be so large. Okay, so this is a statement about rational functions in one variable that we could then bring into the multivariate case for polynomial neural networks. Okay. So in my time remaining, let me shift gears to the equi-width setting. So the equi-width setting, I'll tell you about in a moment, and then I'll go into future directions. So equi-width, as the name implies, all layers have the same width. So here's an equi-width polynomial neural network. You can make it deep if you wanted to, stack these on together. And our result for equi-width neural networks is as follows. So let's say your equi-width neural network has L layers, and the neurovarieties dimension is L times D squared minus L minus 1 times D. And this is the expected dimension by the formula in the definition. Now this holds for all R greater than 1. So long as you're not trying to look at linear functions, you have honest to goodness nonlinear polynomial functions in your neuromanifold, then we know the expected dimension of an equi-width neural network. So there's some good news, bad news, and more good news, my perspective. So the good news is we know the dimension of equi-width neurovarieties. Yay. The bad news is our bound that we had earlier for in general is far from being tight. But the good news is that this leads to now a bunch of new cool problems for an architecture by architecture approach for studying polynomial neural networks. So one illustration of this idea was previously done already with the Alexander-Hershowitz theorem. So this was highlighted in Khalil, Traeger, and Buna's paper, as well as in the paper by Jai Li, Kaya Kubias, and Max Weissman. So this Alexander-Hershowitz theorem is a theorem in algebraic geometry, and this translation relates to neural network, the dimension of neuromanifolds in a shallow case. So how you can view this result is saying that it motivates a lot of new questions that are Alexander-Hershowitz-like. Say a little bit on the remark of the proof. So for the proof, we leveraged the fiber dimension theorem in algebraic geometry. So this theorem says that if you have a map, F, taking X to Y, involving irreducible varieties, then you can do some prediction about the dimension based on the dimension of the fiber. I won't go into details about it. Don't want to do an algebraic geometry course in one slide, but that was the main idea in the proof. Since this work came out, so you see here, this is theorem 1.25. This is from Shafarevic's textbook in algebraic geometry. Since this work came out, a new textbook came out by Emily Plater and Dustin Ross, and this fiber dimension theorem appears at the very end. And so if you're interested in getting into this subject, and you're starting from scratch, the nonlinear algebra, I think this could be one avenue of entry. So follow-ups in the future. So I think I might finish early, but that's okay. We have plenty of times for questions, and we'll get to it. So one thing that I'm really interested in is invertible polynomial neural networks. And so we started looking at this past summer, finding invertible polynomial maps architecture by architecture. So here is a polynomial map taking it's in two variables. So we have X and Y mapping to this X squared plus X plus Y and X squared plus 1. Now, why do I think this is a cool map? It's a cool map because it is invertible. So here it is, if we consider this as the domain, and if we take a line through the origin, this polynomial map takes this line to a curve down here. It takes another line through another curve down here. And so it turns out you sweep out, as you rotate this line in the domain, you get the entire source space. And you can undo this using this polynomial map, uv to u minus v for the first coordinate and v minus u minus v squared in the second. So invertible polynomial maps. Well, you can express these polynomial maps as polynomial neural networks. So in the first part of this talk, the bias was always 0. Here we need the bias to be non-zero. And so here I've expressed this polynomial map as this polynomial neural network. So what we can do is, if we wanted to, is we could take convex combinations of our weight matrices, and we'll get a surface of a neural surface. So here we have our first polynomial neural network. Here's our first weight matrix, and our second weight matrix of that polynomial neural network. Here's our second polynomial neural network. It has its first weight matrix and second weight matrix, and we take convex combinations of these pairs of matrices, apply the parameter map, and when we do that, we get a surface, which is purple here. So what's going on in this purple surface? Well, we have an invertible polynomial function given by this gray point here, and that corresponds to this first map. We have another invertible polynomial neural network given here. This corresponds to the second map that we saw earlier. The convex combinations encompass this space, purple space, and each point on this purple space corresponds to a polynomial map. This polynomial map is going to be degree at most 2. Now, what's cool is that every point along this line corresponds to a polynomial function with non-zero constant determinant. Non-zero constant Jacobian determinant. So here we have a polynomial map. We can look at the Jacobian of this polynomial map. So this gives us a 2 by 2 matrix. We can ask, what is this determinant of this 2 by 2 matrix? And it's going to be a constant. So along this orange line, we have constant determinant Jacobian matrix. Moreover, on this green and these red curves, we also have constant determinant of the Jacobian matrix. But these Jacobians are 0. These are actually going to be constant functions. So what's happening is this green curve actually corresponds to a constant function in this space of polynomial maps. This red curve is another constant function. But if we take an orange point that isn't living on this red or green curve, then it's going to be an invertible polynomial map that is not, an invertible polynomial map. And this is true in general, so long as you believe the Jacobian conjecture. So part of the future work is, well, we're not going to try to prove the Jacobian conjecture, which is the famous conjecture, in algebraic geometry. Instead, we're leveraging all the work that has gone into solving the Jacobian conjecture to understand these invertible polynomial maps. But now, instead of representing a polynomial function as a sum of monomials, we want to see what happens when we represent your polynomial function as a polynomial neural network. All right, so why do we care about this? And so one reason that we care about this is because if you try to train a neural network and to be an invertible neural network, what can sometimes happen is that you end up learning a linear map. Well, linear maps are all well and good. We know when they're invertible and not, but we want nonlinear invertible maps. And this is one of the benefits of algebraic geometry, is that there's a wealth of knowledge of trying to understand these invertible nonlinear maps. So that's one future direction that we're looking into. Oops. All right, so there's been a lot of recent results and new work on what are called rational neural networks. And so in particular, there's this paper, Identifiability of Deep Polynomial Networks, by these authors here, who give better bounds than what we provided for the activation degree thresholds in some cases, not in the equi-width, but in many cases. And then they also don't restrict to the homogeneous setting. They can look at polynomial neural networks that have biases as well. In terms of rational neural networks, there's recent work that came out by Alex Grostos, Elena Robeva, and Max Zubkov, and they have a conjecture also on the dimension of their neural manifolds. And one I hope is true is that you can replicate a proof that involves these Wronskian matrix ideas that went into this PNN work for rational networks. And so that's one hope for the future. In terms of optimization and additional references, so today I focused on describing the space of functions that a polynomial neural network can just produce exactly. You could ask other questions such as, what can they approximate? Or you can ask, well, how do you train a polynomial neural network? And many of these ideas of training a polynomial neural network or training some type of neural network that involves algebra, this comes back to an algebraic optimization idea. And there are many works in the SciAm algebraic geometry community and just SciAm community in general that have gone into understanding these types of problems. Some of them, I only picked a handful here, and there's many more, and people in this audience as well have studied these. Well, shameless advertisement is on metric algebraic geometry going global. So in spring 2027, there will be an ICERM program during that semester from January to March that involves this idea, metric algebraic geometry. And one of the themes of this program is going global. So we saw a hint of this going global idea of these global invariants to describe the neural manifold in terms of finding polynomial equations that describe the neural manifold. So I gave you the dimension, but I didn't tell you equations that actually cut out the neural manifold. And so this is something of future work and people are interested in because it helps lead to algebraic optimization and training these polynomial neural networks. Here, this picture actually doesn't represent PNN. This is related to attention models and some of Kathleen's work. But some of the ideas in this program are going to be related in training or just using algebraic optimization in general for understanding these machine learning and AI models. So that's just one part of this program. There are two other main parts related to geometric data sampling and random geometry, but I won't speak about those at this moment. Keep it focused on this part. Yes, so if you're interested in attending this program, please, the applications are open, so feel free to apply. If this is way in the future, the program is already done, feel free to look at all the amazing YouTube videos and preprints that have come out. So I have a couple minutes left. So one cool thing that came out in this project, this is more of a math and number theory related part, is this idea of a ticket. So Bruce Resnick has this paper on linear patterns of linear dependence of powers of polynomials. And so say you have a polynomial map F. So here I have F1, F2, dot, 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 F capital R. So I have capital R many polynomials. What I can ask is, let's look at the powers, capital M, where if I raise each of these F's to the nth power, I could ask, is this new set of polynomials linearly dependent or not? Immediately, you see the connection to this polynomial neural network setting, because this is somewhat in how, or this is how some of the proof techniques involved these ideas. In either case, Bruce asked the question, for which sets are exhibited as tickets of a polynomial map? And so this is completely wide open. Which subsets of the integers are actually realized by tickets of some polynomial map? And so this was previously studied. And so one thing that might be familiar to you is this is Fermat's last theorem for non-constant polynomials. And so this was proved by Louisville, and the ticket of 3 polynomials is always going to be either 0, 1, or 2. So, but more generally, who knows what happens? So one of the original approaches to this polynomial neural network world that we were originally considered in the first draft of the paper involved this idea of tickets and looking at curves and Fermat hypersurfaces. We weren't able to push this further to the end, but this might be another alternative approach to these types of problems. So with that, I'll finish 4 minutes early. And thank you so much for your attention, and happy to take questions. Yeah, thank you. Bye.
Let's